Welcome back. In this chapter, we examine that the Cartesian graph of any quadratic equation ax square plus bxy plus cy square plus dx plus ey plus f is equal to 0, equation number 1, in which a, b and c are not all 0 is nearly always a conic section. The exceptions are the cases in which there is no graph at all or the graph consists of two parallel lines. It is conventional to call all graphs of equation 1 curved or not quadratic curves. The cross product term. We note that the term in equation 1 did not appear in the equations for the conic sections discussed in the previous chapter. This happened because the axis of the conic sections ran parallel to, in fact, coincides with the coordinate axis. In the next example, we see what happens when the parallelism is absent. Example 1. Example of a hyperbola whose equation contains xy term. Determine equation for the hyperbola with a is equal to 3 and foci at f1 minus 3 minus 3 and f2 3 3. Solution. Let p of xy be a point on the given hyperbola. Then the equation modulus of p f1 minus p f2 is equal to 2a becomes modulus of p f1 minus p f2 is equal to 2 into 3, which is equal to 6, and square root of x plus 3 whole square plus y plus 3 whole square minus square root of x minus 3 whole square plus y minus 3 whole square is equal to plus or minus 6. We move one radical to the right hand side, square, solve for the radical that still appears and square again, and then the above equation reduces to 2xy is equal to 9, equation number 2. A case of equation 1 in which the cross product term is present. The asymptotes of the hyperbola in equation 2 are the x and y axis, and the focal axis makes an angle of pi by 4 radians with the positive x axis. Remarks. As in the previous example, the cross product term is present in equation 1 only when the axes of the conic are tilted. Rotating the coordinate axis to eliminate the cross product term xy. Consider the usual Cartesian coordinate system with mutually perpendicular x and y axis. Let P be a point with the Cartesian coordinate xy based on the x and y axis. We now form new axis obtained by rotating the x and y axis at an angle alpha in the counterclockwise rotation. Then from figure 2 we obtain x is equal to OM is equal to OP cos theta plus alpha, which is equal to OP cos theta cos alpha minus OP sin theta sin alpha, equation number 3. Y is equal to MP is equal to OP sin theta plus alpha, which is equal to OP cos theta sin alpha plus OP sin theta cos alpha, equation number 4. Since OP cos theta is equal to OM dash is equal to x dash and OP sin theta is equal to M dash P is equal to y dash. The equations in 3 reduce to the following. X is equal to x dash cos alpha minus y dash sin alpha, equation number 5. Y is equal to x dash sin alpha plus y dash cos alpha, equation number 6. Equation 5 and 6 are the equations for rotating coordinate axis. Example 2. The x and y axis are rotated through an angle of pi by 4 radians about the origin. Find an equation for the hyperbola in the new coordinates. Solution. Since cos pi by 4 is equal to sin pi by 4 is equal to 1 by root 2, using equations 5 and 6, we obtain x is equal to x dash minus y dash by root 2, y is equal to x dash plus y dash by root 2. Substituting these into the equation 2xy is equal to 9, we obtain 2 into x dash minus y dash by root 2 into x dash plus y dash by root 2 which is equal to 9. X dash square minus y dash square is equal to 9. X dash square by 9 minus y dash square by 9 is equal to 1. Example 3. Suppose that the axis of an xy coordinate system are rotated through an angle of theta is equal to 45 degree to obtain an x dash y dash coordinate system. Find the equation of the curve x square minus xy plus y square minus 6 is equal to 0 in x dash y dash coordinates. Solution. Substituting sin theta is equal to sin 45 degree is equal to 1 by root 2 and cos theta is equal to cos 45 degree is equal to 1 by root 2 yields the rotation equation x is equal to x dash by root 2 minus y dash by root 2 and y is equal to x dash by root 2 plus y dash by root 2. Substituting these into the given equation yields x dash by root 2 minus y dash by root 2 whole square minus x dash by root 2 minus y dash by root 2 into x dash by root 2 plus y dash by root 2 whole square plus x dash by root 2 minus y dash by root 2 whole square minus 6 is equal to 0. Or x dash square minus 2x dash y dash plus y dash square minus x dash square plus y dash square plus x dash square plus 2x dash y dash plus y dash square by 2 is equal to 6. Or x dash square by 12 plus y dash square by 4 is equal to 1, which is the equation of the ellipse. Example 4. Find the new coordinate of the point 2, 4 if the coordinate axes are rotated through an angle of theta is equal to 30 degree. Solution. Using the rotation equations with x is equal to 2, y is equal to 4, cos theta is equal to cos 30 degree which is equal to root 3 by 2 and sin theta is equal to sin 30 degree is equal to 1 by 2, we obtain x dash is equal to 2 into root 3 by 2 plus 4 into 1 by 2 which is equal to root 3 plus 2. Y dash is equal to minus 2 into 1 by 2 plus 4 into root 3 by 2 which is equal to minus 1 plus 2 root 3. Thus, the new coordinates are root 3 plus 2 minus 1 plus 2 root 3. Eliminating the cross product term, the new quadratic equation obtained by rotation. The examples in the previous session showed that suitable rotation of axis eliminated the xy term, thereby reducing the equation to a familiar form. The following theorem tells us how to determine an appropriate rotation of axis to eliminate the cross product term of a second degree equation in x and y. Theorem 1. If the equation ax square plus bxy plus cy square plus dx plus ey plus f is equal to 0, equation number 7, is such that b not equal to 0 and if an x dash y dash coordinate system is obtained by rotating the xy axis through an theta angle satisfy cot 2 alpha is equal to a minus c by b, equation number 8. Then in x dash y dash coordinates, equation 8 will have the form a dash x dash square plus c dash y dash square plus d dash x dash plus e dash y dash plus f dash is equal to 0, equation number 9, an equation not involving the cross product term. Proof. If we apply equations 5 and 6 to the quadratic equation 7, we obtain a new quadratic equation a dash x dash square plus b dash x dash y dash plus c dash y dash square plus d dash x dash plus e dash y dash plus f dash is equal to 0, equation number 10. The new and all coefficients are related by the equations a dash is equal to a cos square alpha plus b cos alpha sin alpha plus c sin square alpha, equation number 11. b dash is equal to b cos 2 alpha plus c minus a sin 2 alpha. Equation number 12. C dash is equal to a sin square alpha minus b sin alpha cos alpha plus c cos square alpha. Equation number 13. D dash is equal to d cos alpha plus e sin alpha. Equation number 14. E dash is equal to minus d sin alpha plus e cos alpha. Equation number 15. F dash is equal to f. Equation number 16. These equations show, among other things, that if we start with an equation for a curve in which the cross product term is present, b not equal to 0, we can find a rotation angle alpha that produces an equation in which no cross product term appears, so that b dash is equal to 0. To find alpha, we set b dash is equal to 0 in equation 12 and solve the resulting equation. B cos 2 alpha plus c minus a sin 2 alpha is equal to 0 for alpha. In practice, this means determining alpha from one of the two equations, cot 2 alpha is equal to a minus c by b, or tan 2 alpha is equal to b by a minus c. Equation number 17. Example 5. Find a quadratic equation that is absent of xy term and represent the curve 2x square plus root 3xy plus y square minus 10 is equal to 0. Solution. The coordinate axes are to be rotated through an angle alpha to produce an equation for the curve 2x square plus root 3xy plus y square minus 10 is equal to 0 that has no cross product term. We find alpha and the new equation. Comparing with equation 7, the equation 2x square plus root 3xy plus y square minus 10 is equal to 0 has a is equal to 2, b is equal to root 3 and c is equal to 1. We substitute these values into equation 7 to find alpha. Cot 2 alpha is equal to a minus c by b, which is equal to 2 minus 1 by root 3, which is equal to 1 by root 3. From the right triangle in figure 4, we see that one appropriate choice of angle is 2 alpha is equal to pi by 3. So, we take alpha is equal to pi by 6. Substituting alpha is equal to pi by 6, a is equal to 2, b is equal to root 3, c is equal to 1, d is equal to e is equal to 0 and f is equal to minus 10 into equations 11 to 16 gives a dash is equal to 5 by 2, b dash is equal to 0, c dash is equal to 1 by 2, d dash is equal to e dash is equal to 0, f is equal to minus 10. Equation 10 then gives 5 by 2 x dash square plus 1 by 2 y dash square minus 10 is equal to 0, or x dash square by 2 plus y dash square by 20 is equal to 1. The curve is an ellipse with foci 0 plus or minus 2 root 5 on the new y dash axis. Figure 5. Example 6. Identify and sketch the curve xy is equal to 1. Solution. As a first step, we will rotate the coordinate axis to eliminate the cross product term. Comparing the given equation, we have a is equal to 0, b is equal to 1, c is equal to 0. Thus, the desired angle of rotation must satisfy cot 2 theta is equal to a minus c by b, which is equal to 0 minus 0 by 1, which is equal to 0. This condition can be met by taking 2 theta is equal to pi by 2 or theta is equal to pi by 4, which is equal to 45 degree. Substituting cos theta is equal to cos 45 degree is equal to 1 by root 2 and sin theta is equal to sin 45 degree is equal to 1 by root 2 yields x is equal to x dash by root 2 minus y dash by root 2 and y is equal to x dash by root 2 plus y dash by root 2. Substituting these in the equation, xy is equal to 1 yields x dash by root 2 minus y dash by root 2 into x dash by root 2 plus y dash by root 2 is equal to 1, or x dash square by 2 minus y dash square by 2 is equal to 1. which is the equation in the x dash y dash coordinate systems of an equilateral hyperbola with vertices at root 2, 0 and minus root 2, 0 in that coordinate system. Example 7. Identify and sketch the curve 153x square minus 192xy plus 97y square minus 30x minus 40y minus 200 is equal to 0. Solution. We have A is equal to 153, B is equal to minus 192 and C is equal to 97. So, cot 2 theta is equal to A minus C by B is equal to 56 by 192, which is equal to 7 by 24. Since theta is to be chosen in the range 0 less than theta less than pi by 2, this relationship is represented by triangle. The hypotenuse of the right angled triangle is given by square root of 24 whole square plus 7 square is equal to square root of 576 plus 49, which is equal to square root of 625, which is equal to 25. From the triangle, we obtain cos 2 theta is equal to 7 by 25, which implies that cos theta is equal to square root of 1 plus cos 2 theta by 2, which is equal to square root of 1 minus 7 by 25 divided by 2, which is equal to 3 by 5. Sin theta is equal to square root of 1 minus cos 2 theta by 2, which is equal to square root of 1 plus 7 by 25 by 2, which is equal to 4 by 5. Substituting these values in 10 yields the rotation equation x is equal to 3 by 5 x dash minus 4 by 5 y dash and y is equal to 4 by 5 x dash plus 3 by 5 y dash, and substituting these in turn in the given equation yields 153 by 25 into 3x dash minus 4y dash whole square minus 192 by 25 into 3x dash minus 4y dash into 4x dash plus 3y dash plus 97 by 25 into 4x dash plus 3y dash whole square minus 30 by 5 into 3x dash minus 4y dash minus 40 by 5 into 4x dash plus 3y dash minus 200 is equal to 0, or x dash square plus 9y dash square minus 2x dash minus 8 is equal to 0. Completing the square yields x dash minus 1 whole square by 9 plus y dash square is equal to 1, which is the equation in the x dash y dash coordinate system of an ellipse with center 1, 0 in that coordinate system and semi-axis A is equal to 3 and B is equal to 1. Possible graphs of quadratic equations. Since axis can always be rotated to eliminate the cross product term, there is no loss of generality in assuming that this has been done and that our equation has the form ax square plus cy square plus dx plus ey plus f is equal to 0. Equation number 18. Equation 18 represents 1. A circle if a is equal to c not equal to 0. Special cases, the graph is a point or there is no graph at all. 2. A parabola if equation 18 is quadratic in one variable and linear in the other. 3. An ellipse if A and C are both positive or both negative. Special cases, circles, a single point or no graph at all. 4. A hyperbola if A and C have opposite signs. Special case, a pair of intersecting lines. 5. A straight line if A and C are 0 and at least one of D and E is different from 0. 6. 1 or 2 straight line if the left hand side of equation 18 can be factored into the product of two linear factors. The discriminant test. Consider the equation ax square plus bxy plus cy square plus dx plus ey plus f is equal to 0. Equation number 19. To verify what kind of conic section the equation 19 represents, it is not required to eliminate the xy term from the equation. We can apply the following. As we have seen, if b not equal to 0, then rotating the coordinate axis through an angle alpha that satisfies the equation cot 2 alpha is equal to a minus c by b. Question number 20. We'll change equation 19 into an equivalent form. A dash x dash square plus c dash y dash square plus d dash x dash plus e dash y dash plus f dash is equal to 0. Equation number 21. Without a cross product term. Now, the graph of equation 21 is a real or degenerate. A. Parabola if a dash or c dash is equal to 0. That is, if a dash c dash is equal to 0. B. Ellipse if a dash and c dash have the same sign. That is, if a dash c dash greater than 0. C. Hyperbola if a dash and c dash have opposite sign. That is, if a dash c dash less than 0. It can also be verified from equations 11 to 16 that for any rotation of axis, b square minus 4ac is equal to b dash square minus 4a dash c dash. Equation number 22. This means that the quantity b square minus 4ac is not changed by a rotation. But when we rotate through the angle alpha given by equation 20, b dash becomes 0. So, b square minus 4ac is equal to minus 4a dash c dash. Since the curve is a parabola, if a dash c dash is equal to 0, an ellipse if a dash c dash greater than 0, and a hyperbola if a dash c dash less than 0. The curve must be a parabola if b square minus 4ac equal to 0, an ellipse if b square minus 4ac less than 0, and a hyperbola if b square minus 4ac greater than 0. The number b square minus 4ac is called the discriminant of equation 19. Method of determining the nature of the quadratic curve, the discriminant test. The quadratic curve ax square plus bxy plus cy square plus dx plus ey plus f is equal to 0 is a parabola if b square minus 4ac equal to 0, b an ellipse if b square minus 4ac less than 0, c a hyperbola if b square minus 4ac greater than 0, provided degenerate cases may not arise. Example 8. A. 4x square minus 8xy plus 4y square plus 5x minus 3 is equal to 0 represents a parabola because b square minus 4ac is equal to minus 8 square minus 4 into 4 into 4 which is equal to 64 minus 64 which is equal to 0. B. 2x square plus xy plus y square minus 1 is equal to 0 represents an ellipse because b square minus 4ac is equal to 1 square minus 4 into 2 into 1 which is equal to minus 7 less than 0. C. 3xy minus y square minus 5y plus 1 is equal to 0 represents a hyperbola because b square minus 4ac is equal to 3 square minus 4 into 0 into minus 1 which is equal to 9 greater than 0. Example 9. Use the discriminant to identify the graph of 8x square minus 3xy plus 5y square minus 7x plus 6 is equal to 0. Solution. We have b square minus 4ac is equal to minus 3 square minus 4 into 8 into 5 which is equal to minus 151. Since the discriminant is negative, the equation represents a point, a line, a pair of parallel lines, a pair of intersecting lines or has no graph. We say that equation represents a degenerating conic section. Thus, if we allow for possible degeneracy, it follows from theorem 1 that every quadratic equation has a conic section as its graph. Now, let us summarize what we have discussed in this unit. First, we discussed the Cartesian graph of any quadratic equation. Next, we move on to the cross product, elimination of cross product by the rotation of the coordinate axis. Discussed a theorem through various examples that every quadratic equation has a conic section as its graph. Before moving to the next session, let us try to answer these questions. use the discriminant b square minus 4ac to decide whether the equations represent parabolas, ellipse or hyperbola. X square minus 3xy plus y square minus x is equal to 0. 3x square minus 7xy plus root 17y square is equal to 1. Find the sine and cosine of an angle through which the coordinate axis can be rotated to eliminate the cross product term from the equation 14x square plus 16xy plus 2y square minus 10x plus 26,370y minus 17 is equal to 0. Do not carry out the rotation. Solve the equation xy plus 2x minus y is equal to 0 for y and sketch the curve as the graph of a rotation function of x. Hope you enjoy the session. See you next time. Till then, goodbye.